These are APA102 strip LEDs. I've never used them before and we're going to figure them out together, looking at the datasheet and writing some code. By the end of this video, I guarantee you'll understand these things inside and out. So here is our LED strip, which has arrived on a black plastic reel. I guess yours will be on a reel too. It seems to be the best way to package it without risking bending it and causing any damage. The first thing I noticed was how sparsely spaced the LEDs are on this strip, and you can get them more densely populated, which in the end I think will be more suitable for what I want to do with it, but just for learning this is going to do us fine. Strips like this one, which is sparsely spaced, I guess would be more suitable for mood lighting an entire room, or something that requires covering a lot of area. Just having a look at the ends of this strip, I can see that there are 4 wires coming out of a connector and another 2 wires. I have a feeling all of the red and black wires are connected, which means we have in total 4 things to worry about, which will be power and ground, and 2 wires which we'll use to control the LEDs somehow. There's a connector on the end here. I guess this is for chaining LED strips. If you want to connect multiple LED strips together, we won't need to do that, but we're going to need to figure out how to connect it to our Arduino. So let's put that back on there. Now what about a close look at one of these LEDs? Let's zoom in. Here we are. I've deliberately lit this from one side so we can see all of the traces. So what have we got? Well, it matches up with the schematic here on the right. We have 5 volts going from left to right. That connects straight through and goes to every LED. We've got 2 inputs here, CKI and SDI. That's going to turn out to be a clock and a data pin. And then we have ground. Ground's going across the top, and I think it connects underneath the footprint of the LED to the ground pin, which is in the bottom left. One important thing to note is that 5 volts and ground are connected to every LED directly. The data and the clock which we're going to send only connects to the first LED, and then each LED is going to relay that information on its output pins. More on that later. Out of sheer curiosity, let's get the microscope out and have a close-up look. Here's our silicon, and we can see the little wires connecting the silicon to the pads, which eventually go to our pins, our input and output pins. If we shift the scope down a little bit, we can see the 3 LEDs. So that should be the blue LED on the left, the red in the middle, it's obviously red, and the green one on the right. No reason to do this other than it's cool to look at things under the microscope, although it does show us that it's 3 separate LEDs which we're going to have to control with our control signals from the Arduino. So how are we going to connect our Arduino to this strip? Well, there are 2 ends to the strip. One end has this handy connector on, and the other end just has 3 wires. If you're following along, just don't follow along for a second because I'm about to make a mistake. My idea was that I could use this connector to connect to the Arduino because I can simply use some jumper wires poked into the end and then poked into the sockets on the Arduino. That would have worked really nicely. We'll find out why it doesn't work in a second. This is the Arduino I'm going to use. It's an old Arduino Mega, but of course you can use any Arduino that has a couple of digital output pins on it. This is just a handy one for me to mess about with because I can do all sorts with it. So I'm looking for 5 volts. These LEDs need 5 volts. That is what is on the datasheet. I'm looking for ground. There's ground. I'm going to pick 2 digital pins. I'm using 52 and 53 because they're on the left hand side of the board. This would have been super neat. As you can see, I've connected it into the connector, but I realized that this connector's at the end of our LED strip. If you remember what I mentioned, and looking at the datasheet here, we need to control the data in and the clock in. The data out and the clock out are controlled by the LEDs themselves, so it's no use me connecting to the data out and the clock out pin of the last LED in the strip. That's not going to allow us to control the strip. In fact, let's demonstrate that. We'll get the multimeter out on continuity mode, and that's ground. That's connected straight through. What about 5 volts? Yeah, that connects straight through, so we could connect to them at the other end of the strip, but as you can see, the clock in and the clock out do not have continuity, they're not connected, neither do the data in and data out signals. So here we are at the correct end of the strip. I'm going to connect this connector on here, and what this gives us is 4 bare wires at the end here. Red is 5 volts, black is ground, and we have green and yellow, which will be the data and the clock signals. So I'm just going to strip these back a bit and tin the ends so I can plug them into the Arduino sockets. We do also have these extra power and ground wires. I'm just going to chop the ends off here because they've arrived exposed and I'm not using them. I don't want to accidentally short anything out. So let's plug it all back in. I've moved ground down to there because it would actually fit after I'd tinned it. I couldn't get it into the socket on the top left. That's the only reason I've done that. And you see I've got the green wire in 52 and the yellow wire in socket 53. So let's plug in our Arduino and then we can start taking a look at the datasheet. So other than the 5 volts required on the voltage in, this is the next most important thing for me to look at. It shows you how we're going to send data to the LEDs. As you know, we only have 2 inputs that we can control. One is the clock and one is the data in. So it looks like we need to control the clock signal by moving it from high to low to high to low and so on. And by high and low we just mean 5 volts and 0 volts. Then we need to control the data in signal by setting it to whatever we want it to be in time with the clock signal. If you're wondering what the 2 lines crossing over mean on the data in trace, that just means the value changes to whatever we want it to be on the next clock cycle, and that could be high or low. Also, the numbers in there 76543210 are just bits of a byte, so we're going to be working in bytes and we're going to be sending 8 bits per byte, as you would. Okay, so what can we take from this? Well, this bit where the clock signal goes from high to low is called a falling edge. That's what we would refer to it as. And you might notice that it coincides with the data in value changing. All this means is that the data in value changes. It might not even change, it might stay high if we want to send 2 ones in a row. So falling edge equals change data in. You might also refer to that as setting up data in or setting up the data bit. Okay, what happens next? Well, our clock signal goes high again. I've highlighted one of those here. The arrow there is the rising edge. And what happens on the rising edge? Well, data in is now steady, it's set up. It refers to here, so in this example it's bit 6 of our data byte, and that is when the data bit is read by the LED circuit. So all we need to do is we need to set the clock low when we are changing our data in value, and then we set it high in order to read that into the circuit, and we repeat the process for all of the bits of data we want to send. Now, I wanted to know about this clock. Clocks have a frequency. I wanted to know what frequency it had to be. And I made a mistake. I looked here where it says oscillator frequency 800 to 1200 kilohertz, and I did some funky code with the Arduino to generate an 800 kilohertz clock that I then tried to synchronize the code to. Well, that turned out to be a complete waste of time. I totally misunderstood how the clock works. Actually, the clock doesn't need to have a steady frequency or a fast frequency. We can just control it up and down whenever our code is ready to do so, and the LEDs will behave correctly. So don't worry about generating a clock. We're just going to set it high or low manually with our code whenever we're ready to do so. So we're ready to look deeper into the datasheet and learn about what data we need to send to make these LEDs do what we want. Before we go any further, I just want to take a minute to say thank you to this video sponsor, PCBWay. Go and check them out. They've got a big Christmas event on right now between December 12th and December 31st. They'll also be running a New Year's event in case you missed this one. There's all kinds of offers going on, coupons and free prototypes, Christmas sales, even some cool boxes you can unbox. The coupons are down here. You can save a certain amount per order depending on the value of the order, and as you know, I use these for my prototype PCBs. I've been using them for the logic analyzer interface, and I'm going to be using them if I hopefully get round to turning this project into an interface for the ZX Spectrum. So go and check out PCBWay and see if their Christmas sale this year has anything for you. So as I mentioned earlier, we've got data in and clock in that we need to control, nothing else. So I'm hoping as long as we're methodical and take this slowly, we'll be able to figure this out fairly easily. This is the part of the datasheet which you might already have seen, which describes the data we need to send to the LED. You may notice this is given in terms of frames, bytes and bits. A frame is just a few bytes of data. Bits, well, is 8 bits in a byte, and that's all we need to know. So let's have a look at the start frame. This is the first data that we should send from our Arduino, and let's see how it's defined. Well, it says 0 times 32, and if we look at the line below, we can see 32 bits as the start frame. That's 4 bytes, all of which are populated entirely with zeros. So our start frame requires us to send 0 32 times. If you remember this diagram, all that means is that we hold data into 0 while we cycle the clock 32 times from low to high. That will be our start frame sent, which means we can move on to the LED frame, or the first LED frame. We have to send one frame of LED data for each LED in the strip, and that's the data field, which goes all the way up to LED N, where N is the number of LEDs that you're using. So what constitutes an LED frame? Well, we start, according to this, with 3 bits, all set to 1, and then we move on to this section called global, which is another 5 bits to complete our first byte, and global, whatever that is described in this table. And it looks like we can populate it with any value from 5 zeros all the way up to 5 ones, and that affects the driving current or the brightness of the LEDs. So this is basically for setting a master brightness for the LED which we're controlling, in this case LED 1. What follows is 3 bytes of data. These are called blue, green and red. As you might guess, these are related to the blue LED, the green LED and the red LED, which we looked at under the microscope, and you can see in the diagram on the right. So these bytes of data basically represent the R, G and B components of the colour that we want our LED to be. We would set this to all ones for all 3, blue, green and red, if we wanted a white LED, or any mixture we want of the 3 colours, giving us basically control to choose any colour that we want. If you're confused by all these zeros and ones, just remember that each byte of data can be represented by a decimal number between 0 and 255. All you have to do is convert that to binary to get the string of zeros and ones that we need to send out of our data pin. You can find any RGB combinations to get any colour represented in terms of decimal, binary or hex, and just do the conversion. We're going to just start by lighting up these LEDs white, just to make it as simple as possible, so hang in there. Once we finish sending the red data, that completes our LED frame, and that completes the LED frame for LED 1 only. We then have to move on and repeat the whole process, sending these 32 bits for LED 2, 3, 4, all the way up to N, which is the last LED in our strip. Once we've sent that one, we move on to the end frame. Now you might have guessed what's going on here. It says 1 times 32 in the text in the top right. It's actually described at the bottom here. I think that's a typo. It should say end frame 32 bits, and it's just all ones. So just like with the start frame, all we have to do is hold the data pin high and toggle the clock 32 times from low to high to send 32 bits of value 1. Now if you got lost at all there, watch it again or hang in there. We're going to write the code now, which is going to make things even clearer. So let's plug in our Arduino and get a new sketch set up. Sketch is just a simple program, and I'm going to talk you through everything in real time, so get ready to do some coding. Okay, so I started a new sketch in the Arduino IDE, and it's obviously auto-populated with a setup function and a loop function. I'm going to get rid of these comments. I like to have the brackets like this, so I'm just going to enter that down there. Above the setup, we're going to start defining our variables. So we're going to start with our output pins. These are going to be integers. We're going to have a clock pin, which I've put into 52 on the Arduino Mega, and a data pin, which is on 53. Now I want to know how many LEDs are in the strip, and I could just type in 30. I know it's 30, but I want to store this in a variable in case I use a shorter strip or a longer strip with this function in the future. Now we need to define our data bytes, which we're going to be putting through our serial data pin to the LED strip, and they're bytes. That's quite important. We can put that in capitals. So first of all, we have the start frame, which we talked about earlier, and this is going to be a variable of type byte, start byte, and I'm going to populate it with 0. Now obviously that is 1, 2, 3, 4, 5, 6, 7, 8 zeros in binary makes 0 in decimal. So that's 1 byte of our start frame, and we need to send that 4 times, which we'll handle in our code below. After the start frame becomes the LED frame, and as we saw in the datasheet, we start with a global byte of information, and I'm going to fill that with ones. So 255 is decimal, that's FF in hex, or all ones, 8 ones. Similarly, I'm going to make a byte for the blue LED data, 255, and for the green LED, 255, all this is going to do is put all of the LEDs to full brightness, and we should have a bright strip of white lights. So red LED byte as well, 255. And then we have to do the end frame after we've cycled this around for every LED. So we'll output that LED frame 30 times before we get to the end frame. And I'm calling this the end byte with value 255 as well. Now while we're looping around, we're going to need to keep track of which LED we're up to. So I'm going to call that int LED counter. I like to start variable names with a lowercase, so I didn't want to put LED in capitals. You can do it however you like. I started typing the declaration in there. What I should type here is counter for LEDs, and that's an integer LED counter starting with 0. And as we write each byte, we're going to need to count which bit we're up to as we're writing the byte. So I'm going to call counter for bits. I'm going to call integer bit counter. You could just call these I and use I, which is fairly normal, but I like everything to have a meaningful name. I also want to be able to speed up or slow down the execution of the code, so let's call this a delay to slow down the clock. Integer bit delay. Integers, if you don't know, are whole numbers, 0, 1, 2, 3, 4. We can't have any decimals in there. We don't need decimals in there, so this is going to take up a bit less memory. Anything after these two forward slashes is a comment, just so the code is more readable. This doesn't have an impact on the program. So that's all of our variables we're going to need. Now we can do our setup program, setup function. So we want to set the pins as output pins in here. So we use the pin mode function, which is just part of the Arduino library. We'll set the clock pin to output, easy as that. And the only other pin we're going to use is our data pin, and that's also an output. So that's all for the setup function. In our loop function, I like to keep the loop function super clean, and I'm just going to call the output data function, which we're going to define output data now. So we'll run the code, it will declare the variables, run the setup, set the pin modes, and then just start looping around here indefinitely, executing the output data function. The output data function is going to run through all of our different frames, sending all the bytes of data that we need as per the data sheet. I'll define it here, void output data, and I like to have my curly brackets on the next line. I want this to call another function, which I'm going to call send byte, capital S, send byte, and I can live down here. And this is going to have one argument. So that means every time we call this function, we need to send it some data. It's going to be an integer. I'm going to call it byte to write. Good. So now we just need to work down through what the datasheet is asking of us in our output data function. So we'll start with our start frame, and if we recall, that is 32 consecutive zeros, or 4 bytes worth of zeros. And this is really simple for now. All we need to do is send byte, and we will pass it the value of start byte, which is 0, or 8 zeros in binary. And yeah, we're going to need to do that 4 times because we need to send 32 of them. Maybe not the most efficient code, but that works for me. Now we move on to the LED frame, which is another 4 bytes of data. So all we need to do is call the send byte function, pass it the global byte, that was the first byte in our LED frame, and then we send the blue LED byte, capital B. Then we send the green LED byte, green LED byte. We send the red LED byte. And finally, we will need to send the end frame, which was 32 ones, or 4 bytes worth of ones. So we send byte, end byte, and we do that 4 times. I'm just going to copy paste. Now this would only send info to the first LED in our strip, so what we need to do is add a loop here, a for loop. So we define a for loop as for. Our counter, we're using the LED counter in this case, starting from 0 and we're going to loop until LED counter meets number of LEDs. So I'll do LED counter num of LEDs, which we've defined up here as 30. Spelt it wrong. There we go. Num of LEDs. And we increment by 1. So in the third part of this we write LED counter double plus increments it by 1. We have our curly brackets, curly brackets surrounding the LED frame. I'll indent it to be neat. And we'll just comment this up so we know what each of these contains. If we recall, it was 3 ones and then 5 bits to define our brightness. This one is 8 bits of data defining the brightness of the blue LED, and so on and so forth. Brightness of green LED, brightness of red LED. The way I'm looping this means that every LED is going to receive the same data. We can always enhance and evolve the code later, so if we wanted different LEDs to have different colours, we can do that. I think that's possible anyway. Is that our loop? Yeah, that's our loop. So output data is going to send the start frame, it's going to send the LED frame for every LED in the strip, and then it sends the end frame. Nice and easy so far. Now we just need to define the send byte function. Shouldn't be too difficult. This is going to loop 8 times because it's going to send the byte 1 bit at a time. So loop 8 times for the 8 bits in the byte. We're always sending it a byte. We only need to do 8 times every time. So here's our for loop, like above, but this time we're using a bit counter starting from 0, and we're going to go until it equals 8. So in here we write bit counter less than 8, and then we're going to increment it by 1, bit counter double plus, curly brackets. Alright, so let's remember our diagram showing the clock pulses and when to set up the data bits. First we need to induce a negative edge on the clock. So we use the digital write function and we write to the clock pin low. That sets the clock pin low. Previously it would have been high because of the way it's going to cycle up and down. Then we set up a data bit while the clock is low. So we digital write again, this time to our data pin. And what do we want to write to it? We want to write, first of all, the first bit of the byte that we're trying to write, and then as bit counter increments, we want to write the corresponding bit. So what do we write? We use the bit read function, and the bit read function reads a bit out of a byte. So what arguments does it take? It takes the byte that we're trying to write, so it's byte to write, that's what's being passed. Anytime we call it, we send it the byte to write. Either here it's start byte, here it's global byte, whatever. When we're coding inside this function, we always call it byte to write. And which bit of that byte do we want? Well, it corresponds to bit counter. So it starts with 0, it will increment to 1, 2, 3, 4, 5, 6, 7, making our 8 bits of the byte. Next, we need to induce a positive edge on the clock to write the data bit. So we digital write to the clock pin high, and that's going to send the clock high. It's going to latch in the bit into the circuitry within the LED. And I'm going to allow for an optional delay, and I'm going to do this in microseconds. I just want to have more options for it to be super fast. So we delay microseconds with delay, but I think I've just defaulted that to 0 initially. Let's have a look. Bit delay equals 0. Now I have. Alright, lovely. And that's our code. So what this should do is turn on all of the LEDs just as bright as they possibly can be and as white as they possibly can be. So let's give it a try. I've plugged in the Arduino. We can verify it. I made a mistake. I didn't have a capital P on clock pin. Let's try again. Verify. Okay, now it's compiled. We can upload it to the Arduino and can have a look at what it's doing.
Well, there we are. Thankfully it's all white and it's all bright, so the code has worked. That's fantastic. Let's have a closer look. I want to look under the microscope and we can see all 3 of our LEDs, the RG and the B, are all at full brightness. Lovely.
So it appears to be doing what we want, but it's not very interesting, is it? So let's make it cycle between all red, all green and all blue. So if you bear with me, I'll switch back to coding land. One moment please. So we've got it working, but is it really doing what we want it to do? Well, we can mess around with it and make it cycle some colours around. So what if we wanted to illuminate every LED red, blue and green separately and cycle between them? Well, it's really easy to do because we've been patient and we've written nice neat code which we can adapt very simply. I'm just going to run the output data routine 3 times, one for each colour. And I'm copying the LED bytes definitions down here. We don't need to declare the variable type anymore because that's already done. And I need to do this 3 times. 1, 2, 3. Keeping the indent nice and neat. Indent, indent. We'll start with blue, so we'll have the blue LED byte as 255 or all ones, and then we'll turn off the green and the red LEDs by writing 0 to their bytes. And then on the next round we will just have a green set to 1, blue and red set to 0, and then that just leaves red for the last one. We can compile that and write it to the Arduino. Just looking at it now, and oh, it's really fast. Hang on. Let's put a delay in. So mess around with the delay, try some different numbers and see if we can find something that looks nice, and we'll take a look at it on the desk and under the microscope. Wow, look, it's working. That's cool. And they're all changing colour sequentially in a kind of rolling strip, which is what you would expect. I've jammed it under the microscope here so we can have a close-up look at the LEDs all changing. So look at this, we've got blue, green and red. Fantastic, it's doing exactly what we want, so I'm a bit more confident that the code is working correctly. But you know me, I'm going to put the logic analyzer on it and look at the signals moving around just to marry everything up from the code to what's actually happening on the LEDs themselves. That'll be interesting, won't it? So I've got it going really rapidly and I've hooked it up to Gusman B's logic analyzer, which you'll have seen in a previous video. Let's plug that into the PC as well and we can have a look at the traces. So here we are in the logic analyzer software. I've taken this trace of what you saw set up there. This is the data pin for LEDs 1, 2, 3, 4 and 5. I've also added the clock signal from LED 1 because that's required for us to know how many bits we're sending. I'm just going to hide LEDs 2, 3, 4 and 5 for now. We'll just look at the data in the clock pin on the first LED of the strip. I've taken the sample at 800 kilohertz, 800 kilohertz, which should be plenty for us to see propagation delays between the LEDs and things like that. I've taken lots and lots of samples as well. So let me just zoom out a little bit and you start to see the bigger picture. This is the LED data cycling between 1 and 0, and here's our many clock pulses. And I've taken the liberty to highlight some regions for us here. So let me zoom in. You're going to recognize these as our frames of data which we were sending from our Arduino program. If I zoom in here, we'll start here from the setup. So if you remember, the setup was 32 zeros to be sent. If I just measure across here, measure, and go to go to the clock, see there are 32 positive pulses of the clock, all while the data pin is 0, so that means we've sent 32 zeros. That's exactly what we intended with the code. Seems to be working perfectly. That's our setup frame, or our start frame I should say. Then we have the global frame. I just went for maximum brightness here, so we have 8 ones. That's our 3 ones to start the byte, and then the 5 bits all set to 1 for maximum brightness. Now this is running a very fast cycle between blue, green and red. So here's the first case. We have 8 ones sent, and our blue LED byte is part of the LED frame, which is these 4 bytes. and then green and red are set to 0, so we have 8 zeros for green, 8 zeros for red. This is all repeated again, all 4 of these bytes, for LED 2, and this goes on and on for all 30 LEDs. Here's LED 3. We can go all the way across. To help me count, I've highlighted LED 20. Eventually we get to LED 30. So let's zoom in here. This is LED 30, getting its global byte, full brightness on blue, zeros on green and red. Then we reach our end frame. If you recall, that was 32 ones sent. If I do a measure across here and scroll down to the clock data, we have 32 positive pulses, and the data pin was held high all the way throughout, so that's our 32 ones sent as our end frame. Now we're into the next cycle of our output data routine. We have 32 zeros for our setup. Our global is the same, but this time we change blue to 0, green to 1, and red to 0. And we can see it happening here perfectly. This happens 30 times again. We can scroll all the way across till we get to LED 30 and then the end frame. We have our setup frame again, our global frame, and then blue is low, green is low, and red is high. And back to the global, and so on and so on and so on. We can see that our code's working perfectly, and I love seeing it working under the logic analyzer. So here I've zoomed out a little bit, and we can see the data going to LED 1 here at the top. I've restored the views of LEDs 2, 3, 4 and 5. So after LED 1's received its data, we get to the next LED frame. It gets relayed on from LED 1 to LED 2. We can see it here. Same again for LED 3, 4 and 5 and so on all the way up to 30. But we do see some propagation delay. If I zoom all the way in, so here we see some propagation delay. I think this is what you would call propagation delay. I can measure it here. It's just a few samples, 6.25 microseconds as it gets relayed on through each LED to the next LED. I would have liked to use this as a strobe light at some point and switch them all on and off simultaneously, but I can see that that's not possible. It's just not designed to do that. And I don't think that's because of the propagation delay, that's because just of the way they're designed, that the data is relayed on one LED at a time as each frame is passed to it. And that's about it for my basic intro, figuring out the APA102 LED strip. So what do I want to do with it? Well, I love Manic Miner, and Manic Miner has this air gauge at the bottom. It's basically a timer within which you have to complete the level, otherwise it's game over. I really want to get this represented by the LED strip. So I'm going to configure the LED strip to have a green section and a red section, like you can see on the screen here. And I've kind of done that here just to prove the concept, or no, just to prove what it's going to look like. Now the next challenge, which will be the next video, will be to take the data of the remaining air, or the remaining time, from the edge connector of a ZX Spectrum. So we're going to design a little interface to snipe that data off the data bus, and then try and interface it with the Arduino so we can have a massive LED based air gauge for Manic Miner, which is completely pointless but quite a fun project to do. So I'm going to leave you there. I'm going to say Merry Christmas, and I'll see you for the next video, which might be in the new year. Otherwise keep an eye out for more live streams. We'll be playing some more ZX Spectrum games. Cheers then, bye bye.